the last segment, we noted that system stability can be improved by rapid clearance of faults. When the faulty section of line is removed at high speed, there is less likelihood of the generator swinging out of step and losing synchronism. However, when a line is tripped, the system is operating in a weakened condition, and instability may still occur. One way around this problem is to bring the line back into service again as quickly as possible by automatic reclosing of the breakers. This action is based on the fact that most faults on overhead lines are temporary faults caused by a lightning strike or high winds or other climatic conditions. When the breakers are reclosed after, say, half a second, in most cases, the temporary fault will no longer exist. Automatic reclosing is not usually employed on underground cable systems, as these are not susceptible to temporary faults. A fault on a cable system is usually due to a permanent fault in the cable itself. The type of reclosing scheme employed varies according to the function of the line itself. For example, is it a transmission line or a distribution line? Is it close or far away from a generating source? The reclosing relay generally allows for several attempts at reclosure with different time delay settings. On high voltage transmission and sub-transmission lines, we usually want the line to reclose as quickly as possible so as to help maintain stability. This is usually carried out by the instantaneous setting on the reclosing relay. However, a small time delay of about half a second, that is 30 cycles, must be allowed before reclosure so as to permit the arc to extinguish at the fault. At high voltage, say 345 kV, it takes about 21 cycles for the air gap at the fault to deionize. If we reclose the breaker too soon, the fault arc would immediately restrike. To prevent this occurrence, a time delay between opening and closing is usually built into the breaker by the manufacturer. The actual time will depend upon the nominal breaker voltage. In addition to this, a minimum time delay, say 5 cycles, may be added to the instantaneous relay operation. So the total time delay for reclosure may be about 35 cycles. If the fault is still on the line after reclosure, the protection will trip the breaker once again. The recloser may now make a second attempt to reclose after a time delay of, say, 5 seconds. Usually, these relays allow up to 3 or 4 attempts at reclosing. If the fault still remains on after the final attempt, the reclosing relay locks out and the breakers remain open in the tripped position. The reclosing relay will only reset after the breaker has been closed manually or by the SCADA system to restore the line to service with the fault removed, of course. When automatic reclosing takes place, it is essential that both ends of the line remain in synchronism, or at least close to synchronism. This may not be the case, for example, with an interconnecting line between two power systems. If there is a large power flow over the interconnection before tripping occurs, it's likely that the two systems will rapidly move out of synchronism when separated. One system may speed up, while the other decreases its frequency. The phase angle between the two systems will increase rapidly, and they will not remain in synchronism. In this case, automatic reclosure cannot be used. However, in most power systems, there are many transmission lines operating in parallel. Hence, loss of a line will cause the load to transfer to others. In this situation, the two ends of the line will remain in synchronism, but there may well be an increase in phase angle between the voltages at each end. We have already seen the reason for this in earlier segments of this tape. Indeed, this is one reason why reclosure should be as rapid as possible. Incidentally, in order to obtain high-speed reclosing, it is essential that the temporary fault is cleared by high-speed, simultaneous tripping at both ends of the line. This means pilot protection must be used. In this case, high-speed reclosing will be virtually simultaneous at both ends. But remember, if it's necessary to take the pilot protection out of service, it's also necessary to block the high-speed reclosing action. We may run into phase angle problems where the first reclosing attempt fails and the line trips again. The relay then attempts a second reclosure with time delay. In this situation, the phase angle between voltages at either end of the line may be quite wide, and reclosure at this point could cause a shock to the system. How can we get around this? Well, one method is to apply only single-pole tripping and reclosing. Experience shows us that most temporary faults occur on one conductor only, giving us a single phase-to-ground fault. For this reason, many installations choose to trip the faulted phase only. The pilot protection is set up to trip both ends of the line, but on the faulty phase only. For the brief interval of time that this phase is out of service, the remaining two phases will continue to transfer power and so retain synchronism and keep the phase angle difference within a narrow band. The instantaneous reclosing relay will quickly close the breakers again and restore the line to service. Of course, the same protection is set up so that a three-phase fault will trip all three phases at both ends. If single-pole tripping and reclosure is not installed, then another method is to use a Synchro check relay to measure the phase angle difference. In this arrangement, reclosure takes place first at one end of the line only, while the Synchro check is performed at the other end. This relay measures the phase angle of the voltages on either side of the breaker, and it will only allow reclosure if this angle is within a specified limit, say up to 40 or 60 degrees out on the system. Yet another way around this problem of reclosing into a large phase angle difference is to eliminate the second and subsequent reclosing attempts altogether. I am sure that you will find on your system many transmission lines which have reclosing relays, but some of these are limited to only one instantaneous attempt at reclosing. If the breaker trips again, the relay locks out. There are even limitations to the application of the instantaneous reclosing arrangement. This is where the transmission line is located close to one or more large generators. The shock to the generator of suddenly rejecting load, then applying load again, could conceivably cause mechanical stress and ultimate damage to the turbine and generator rotors. For these reasons, and to preserve system stability, instantaneous reclosing relays are usually not installed at locations close to a generator. We can see that the application of reclosing relays depends upon the system location and the specific system. We have mentioned in earlier tapes that when reactors are installed, they are usually connected directly to the transmission line. In this case, automatic reclosing should not be applied. This is because a fault in the reactor is more likely to be permanent than temporary, and we certainly do not wish to reclose and re-energize into the internal fault of the reactor. The same thing goes where a transformer may be directly connected to the line. For distribution feeders, the breaker in the substation is often fitted with a reclosing relay. The first reclosure may be instantaneous, but the second, third, and fourth will each have a time delay of 10 to 20 seconds. In setting the reclosing relay, it's necessary to know the types of load which are supplied by the particular feeder. For example, the feeder may supply an industrial load which includes large induction motors. Reclosure must be delayed until the motors have time to run down and reduce their residual voltage to less than 1/3 of rated. With synchronous motors, it's preferable to trip the motor before restoring the voltage to the line. You'll remember we discussed this matter in an earlier tape. Loss of voltage relays should be installed on all large motors. An even more difficult situation arises where the industrial consumer also generates all or some of his power requirements, and these generators are synchronized into the power system. In this situation, reclosure of the feeder would not be practical, as the two systems would now be out of synchronism, and some damage may occur to the customer's machines. The customer's generator should be tripped before any reclosing takes place on the feeder breaker. On most feeders, there are a large number of fused taps supplying different customers. The protection scheme may be coordinated so that if a temporary fault occurs downstream of any fuse, the feeder breaker protection will operate first. It will instantaneously trip the breaker and then instantaneously reclose again. If the fault remains on, that is a permanent fault, the breaker will not trip the second time, as the instantaneous protection is now blocked. The second attempt at reclosing is delayed sufficiently for the local fuse to operate and clear the permanent fault. On distribution systems, another more direct reclosing arrangement is often used in addition to the reclosing relays that we've been talking about. The device in question is known as a recloser, and it is usually installed in the line itself at some remote distance from the feeder breaker. Several reclosers may be installed, particularly at points where different sections are tapped off. The recloser is essentially a switch with limited capacity for interrupting fault currents. This is acceptable because very high levels of fault current occur closer to the feeder breaker, which has greater interrupting capacity. However, further down the line, fault currents are less, and the local recloser will clear that section of line and then attempt to reclose. The operation of the recloser is mechanical, and usually up to 4 attempts are provided with time delay settings between each attempt. Again, all of the settings need to be coordinated with other protection devices on the feeder, particularly the feeder breaker. Actually, the operation of reclosers on the distribution system does not really affect the stability of the power system very much. They are installed with the objective of reducing outage time to the customers. However, on transmission and sub-transmission systems, it's clear that reclosing schemes can help retain stability of the system and reduce the likelihood of generators or parts of the system falling out of step. But unfortunately, instability can and occasionally does occur.